Check it out now, y'all.
Nano Hub U, online instruction.
Welcome to tutorial 2.2 from week 2. Now, as you know, in this homework 2, what I asked you to do was take a specific energy momentum relation and then try to apply the principles that we developed in the lecture modules. And for the first homework problem, what I'd asked you to do is obtain expressions for this N of E and D of E, the density of states and this total number of states, and show that they obey certain relations. And that's worked out in tutorial 2.1, you see. And what I have up in the blackboard is something we worked out in tutorial 2.1. So, since some of that is needed for this problem, because here what I asked you to do is look at the conductivity expression and try to find an appropriate expression relating the conductivity to the number of electrons. And I'll be making use of some relations back from the tutorial 2.1. So if you haven't watched the 2.1, you could refresh you should go and look at it, because these results that I have up here on the blackboard right now, these were all obtained in 2.1. Okay. And as I explained in 2.1, rather than do all three energy momentum relations, I'll only do this one, because the other two can be obtained as special cases of this by setting EC to 0 or setting EC to some large value. Okay. Now for this particular energy momentum relation then, what we had obtained was this expression for N of E. Now in this homework, what we are interested in is this expression for conductivity that we obtained in the regular lecture, which had the form Q square N, that is the number of electrons per unit area, which you could write as Ns. And this is the usual, and we're trying to relate it to this usual Drude expression, which is that conductivity is Q square times electron density, Q square N times tau, and divided by M. But as we did in the regular lecture, what I had shown was that the result you really get is V tau over P. That is, of course, momentum divided by velocity is like mass, but then in these general energy momentum relations, they are not necessarily all equal. They are not necessarily constant. That is, P over V itself could be changing with energy. So we'll start from this expression, and the next step is that for V, I'll use for this energy momentum relation whatever we had obtained in tutorial 2.1. Namely, V itself is like V0 square P over E. So instead of V, I put V0 square P divided by E. And the P cancels. So basically it is V0 square divided by E. So you'll notice then, instead of mass, we have E over V0 square. So as if E is equal to mv square, mv0 square. Okay. Anyway, so this is the expression that we have. Now what you'd like to do is get an expression for conductivity in terms of the electron density. And usually you tend to think of this as a constant and you say conductivity is proportional to electron density. But that's not true in this case, because as you'll see, this itself can be related to the N. And the way I can do that is, we can start from here and turn this around. So we could write it as, I guess I'll do it over here, E square minus EC square is equal to, so what I'm doing is starting from that expression for n that we had here, I am writing E square minus EC square in terms of the n. So what we get then is and this is, of course, what we are calling the electron density. So E square is equal to EC square plus H square V0 square NS over pi. That's it. So when I take this and I put it back in here, what we get is, in fact, let me use the red pen. Q square tau V0 square and then NS divided by this E, and E is now like the square root of this. So the E is like this. So I'll write it as divided by square root of EC square plus so this would then be the general relationship, you see, between the conductivity and the electron density. And you notice it's not linear. Conductivity is not going linearly with Ns. It's like Ns divided by that quantity. Now you could try out the two special cases I mentioned. So, for example, we could set EC equal to 0, for example. So that would then get us back to the case we discussed in the lecture module, I believe, 2.4. That is, graphene is when we set EC equal to 0. Now if you do that, then you can see, if I put EC equals 0, that drops out. There's a NS here and the square root of NS. So overall you get a square root of NS. See, so you get something like Q square over H from here, and then you get the square root of NS, and what you could work this out, square root of pi NS, etc. And and the constants that go with it. But the point is, this is what we had done in module 2.4, where we got a conductivity proportional to square root of Ns. On the other hand, if you let EC tend to be some very large quantity compared to this, then you can drop this. And then you'd get the usual Drude formula type of thing, what you expect for parabolic relations. That is, if you drop this, this becomes EC, and so what you get is Q square tau NS V0 square divided by EC. And as I had explained in the last module, this module, I guess, the tutorial 2.1, as I had explained in tutorial 2.1, this quantity EC over V0 square can be interpreted as mass, m, in that context. So this then would be the Drude formula, Q square NS tau over m. So just to summarize what I did then, we took this general energy momentum relation and worked out a general expression for conductivity in terms of the electron density. Okay. And of course, this is understood to be at low temperatures, because in general, like this is the expression, this is what you get at a given energy. You have to average over energy using the del F0 del E as we have discussed before. But at low temperatures, this quantity evaluated at the chemical potential, that should give you the conductivity. And so conductivity then is proportional to Ns divided by square root of Ns plus something. And for, I guess, for normal parabolic conductors, you can drop this, and then you get conductivity proportional to Ns. But for graphene, you can drop this, and then you get conductivity proportional to square root of Ns.